Welcome. This is very important module for this particular session of lectures. The reason is because we are today understanding a very important aspect, and that is photolithography. So, what is the purpose of photolithography and why we want to perform photolithography, or why we want to understand photolithography? So, let us take few examples. So that you understand how we can use photolithography for fabricating different devices or different structures on the devices. Now, I am holding one wafer in my hand, right, and it has few patterns. There is another wafer in my hand, again it has few patterns, right. There are two wafers in my hand with few patterns, as you can see, right. Now, how can you design these patterns? The answer is photolithography. Okay. So, we are learning how to perform photolithography. I will show you few more devices just to make sure that we clearly understand what we are learning today. You see, there is a heater on this. If you can zoom in little bit, yeah. So, you can clearly see, or hopefully you can clearly see, there is a heater, right, which is right over here in this area, all right, and these are two contact pads of the heater. Heater is right here, two contact pads of the heater. How can you fabricate this heater? That is the question, all right. How can you fabricate this heater? And we will learn this thing today, all right. And then you will see that in subsequent classes, when we talk about micro engineering devices for clinical perspective, right, how can you fabricate those devices using photolithography. So, let us see on the screen photolithography. Photolithography comes from a word photo and then lithos. So, lithos and graphy is a Greek word used, which means carving from a single stone. The purpose of photolithography is to create, and of course, photo means nothing but photons, light, right, light to carve a single stone. Here in our case is a single crystal, which is silicon. So, anyway, the purpose of photolithography is to create small structures or features on a silicon wafer using photoresist. We will see what is a photoresist. Okay. And features are made out of photoresist by etching with UV light. Okay. So, what we understand, we can create small features. One, we can use silicon wafer, but is not just limited to silicon wafer. We can also use glass, as we have just seen. We can also use an insulator like alumina. There is a polymer involved, and that polymer is called photoresist. This polymer is photosensitive polymer, and we will be using this polymer to create several features by etching the polymer with the help of UV light. So, now when you talk about photolithography, there are several steps involved, and the first among several steps is wafer cleaning. You cannot, or you should not start any process in microengineering without cleaning the wafer. Now, cleaning the wafer does not just mean to clean by clean with DI water, or to dry with nitrogen, or to just pre-bake it. Cleaning of wafer means, like we have discussed in earlier classes, right. We have a wafer, we have a thin layer of oxide, even we do not do anything in air at room temperature, in air there will be thin layer of oxide, few nanometers, right, few nanometers of oxide grown on silicon wafer. So, first thing that you have to do is dip this wafer in HF dip. This is very important. When you perform HF dip, what you will see is the silicon dioxide can be etched from the silicon wafer. After silicon dioxide is etched, then you have to perform the rest of the step, which is cleaning with DI water, deionized water, followed by drying with N2 nitrogen air, right, followed by pre-baking. All right, to remove any moisture on this surface. So, what are the process? First you have to perform HF dip, then you have to clean the wafer or rinse the wafer with the help of DI. After rinsing the wafer with DI, you have to dry the wafer with help of nitrogen. After drying the wafer with nitrogen, you have to pre-bake the wafer to remove any moisture. After this, your wafer is ready for photolithography. So, to perform photolithography, the first step would be, if you see the screen, first step would be pre-bake, we perform pre-baking already, and primer coating. HMDS is one of the primer that we can coat, and this will improve the adhesion of photoresist onto the surface of the substrate. After coating HMDS or primer, the next step is photoresist spin coating. We have to spin coat photoresist, and the thickness of photoresist depends on the RPM and depends on the time, right. How many rotations per minute we have programmed, for how much time we are spin coating the photoresist, based on or depending on RPM and time, we can know or we can determine thickness of the photoresist. So, once we perform spin coating with photoresist, we go for soft bake. Now, in a conventional situation, soft bake is done at 90 degrees centigrade for 1 minute on hot plate. This time would vary if I use oven. After soft baking, I had to perform alignment and exposure. So, I have a wafer, I clean the wafer, and then on this wafer I coat a primer. On the primer, right, I of course pre-bake it and then coat the primer. On that I will spin coat my photoresist. spin coat my photoresist. This is my silicon, this is my primer. After photoresist, I have to get a mask. Let us say this is a mask. We will talk about the mask and photoresist, how it will work depending on its type. Mask are also classified depending on its pattern, that is we will discuss it later. So, this is your mask. You have to align the mask and then perform UV exposure, right. After UV exposure, you have to unload the mask and dip the wafer in a beaker which contains photoresist developer. After developing photoresist, you have to take out the wafer and perform hard baking. Hard baking in a conventional way for conventional photoresist, that is positive and negative photoresist, is performed at 120 degree centigrade 1 minute on hot plate. Let us write it down, on hot plate. After performing hard bake, you can inspect the pattern. After performing hard bake, next step is inspecting the pattern. So, we will take an example, to see what we have discussed right now, okay, so that we understand clearly how photoresist or how photolithography can be used. So, like I said, wafer cleaning and pre-bake can be done by bubble jet, high pressure rinse by sonication. Dehydration or pre-baking can be done at high temperature baking to remove moisture, right, after wafer cleaning process. Priming or primer is used to improve photoresist adhesion. HMDS is used. HMDS is your hexamethyl disilane, and that is used to improve the adhesion of a photoresist onto the substrate. So, what is photoresist? Photoresist is solid organic material. It is used for transferring the design pattern to this wafer surface, changes photosolubility due to photochemical reaction exposed to UV light. Okay. So, let us first understand the role of photoresist. Okay. So, if I say I have photoresist are two types, one is positive photoresist, second is negative photoresist. Okay. Now, let us take an example of this particular pattern. this pattern. Okay. Now, there are two wafers, or let us draw the top view of the wafer rather than cross sectional view. There are two wafers. One wafer is coated with positive photoresist, second wafer is coated with negative photoresist. This is your mask. This is your mask. So, if I use this mask on the photoresist, so I have to. So, what does that mean? If I keep this mask on this wafer like this, and the wafer is coated with positive photoresist, what will happen that when I expose this, I will have, when I expose it to UV light and I develop the wafer, right, in which I use this kind of mask, then I will have my photoresist protected in this area. Okay. So, what do you understand here? What we understand is that the area which is exposed becomes weaker and the area which is not exposed becomes stronger, right. Why? Because our mask was this, right, and we had positive photoresist coated on the wafer, and this wafer if I place under this mask and if I expose it and I develop it, then I obtain this pattern for positive photoresist. In case of negative photoresist, in case of, let us say instead of positive photoresist, we have used wafer which was coated with negative photoresist. Then when I expose with UV light, when I exposed with UV light, what I obtain? I obtain pattern which I am drawing right now. I will obtain a pattern which looks like this. Take one more minute, because it is very important. I do not want to rush it through. Yeah, you see. So, that is if I use negative photoresist, sorry, and I use this mask, then I obtain this kind of pattern, and this pattern means that the area which was exposed gets stronger and the area which was not exposed gets weaker. So, in case of positive photoresist and negative photoresist, we have to remember in positive photoresist the exposed, let us see here, let us write down exposed. Can you see? No, exposed, let us say area exposed becomes weaker. In case of negative photoresist, it becomes stronger. Which one? Area exposed. Okay. In case of positive photoresist, it becomes weaker. In case of negative photoresist, it becomes stronger. You can see here, right? This is the area. If I just remove the mask, remove the wafer, sorry, then you can see this is the area which is not exposed, the area here which is not exposed, remaining area is exposed. So, in case of positive photoresist, what I obtained is the area which was not exposed gets stronger, area which was exposed gets weaker here, correct. In case of negative photoresist, the area which was exposed, this area, this one, this area is exposed, right, is transparent, is exposed. Exposed under what? UV light. Area which was exposed became stronger and area which was not exposed, this is the area which is not exposed, correct. Becomes area which is not exposed becomes weaker in case of negative photoresist. You can see here it becomes weaker. So, photoresist is developed. Photoresist is developed in this area. So, it is very important to understand photoresist because we will be using positive and negative photoresist extensively when we understand photolithography. So, let me show you few more points. Now, what should the photoresist consist of? What is the polymer should have? Polymer should have high etch resistance and good adhesion, that is a requirement, right. And how it is performed, this how the polymer is coated onto the wafer. These are the steps. First, dispense 3 to 5 ml of photoresist. Second, slow spin at 500 rpm, followed by high ramp up to 1100 to 5000 rpm depending on the thickness that you want. Photoresist is spread through centrifugal force and the quality measures for this photoresist can be time, thickness, speed, uniformity. Also we can see particles and defects if any on the photoresist. When we coat the photoresist, we have to take care of this many parameters. Now, if you see here, there is a requirement of slow spin. This slow spin is to uniformly distributed photoresist onto the wafer, and then we ramp it up to 1100 to 5000 rpm, so that we can obtain the thickness of our desire. Now, there are two types of photoresist like we have discussed here, positive and negative type. Negative photoresist can be SU8, it can be N4200, 4300, 44400. Positive photoresist can be AZ3312, it can be from Shipley 1.2 liters or Shipley 1.2. So, like I said, when you talk about photoresist, photoresist are two types. One is positive photoresist, that is exposure to UV light removes this resist, exposure to UV light removes the resist, or exposed region becomes weaker, correct. Negative photoresist, exposure to UV light maintains resist or the exposed region becomes stronger. So, this is a case that if you have a mask, then if I use positive photoresist, I will obtain this pattern. If I use negative photoresist, I will obtain this particular fashion if I use the mask which is shown in schematic here. So, since we were talking about mask, let us see how the mask looks like, how the mask in reality looks like. Okay. So, when we talk about masks, mask can be bright field mask, it can be dark field mask, bright field, dark field, two types of mask, okay? Bright field and dark field mask. So, let us see how bright field mask looks like and let us see how dark field mask looks like. So, I will show it to you. Mask holder, mask is in my hand. So, you do not have to worry about zooming in this time, you just see that I am holding a glass plate, I am holding a glass plate, right. This is a 5-inch mask. Why we are using 5-inch mask? Because we were interested in using a 4-inch wafer. Like this, correct. We were interested in using 4-inch wafer, 4-inch wafer, 5-inch mask. So, whenever you are using wafer, depending on the diameter of the wafer, you have to change the size of the mask. Now, what you see in mask? Can you see my finger? Can you see my face? You can, right? But there is some pattern through which you cannot see, through which you cannot see. So, most of the area in this mask is empty, is transparent. So, this mask is nothing but bright field mask. Field is bright, you see, this field is bright, bright field mask, and there is some pattern on the mask. There is some pattern on the mask with some alignment mark right over here, which you cannot see from there, it is impossible. But the point is, there is a glass, it can be chrome mask, it can be a chrome mask. Now, let us see one more mask. So, you can clearly distinguish what I mean by bright field and dark field mask. This is another mask here, right. What you can see? You can see there are two patterns on the bottom which are transparent, remaining field is dark, remaining field is dark, right. But here on the two bottom you can see some patterns are there. So, this is your dark field mask, this is your dark field mask, it can be used as a mirror, just kidding. So, we have bright field mask and we have a dark field mask. You know guys, in Fab Lab you are wearing a gown and everything, you can see your face in this, just kidding, huh? Do not do that. So, this is your bright field mask, this is your dark field mask, very easy to identify, no, it is very easy. Okay. So, both are 5-inch mask. So, coming back to the screen, photoresist, positive, negative, mask, bright field, dark field. So, how can we spin coat photoresist onto a silicon wafer, right. So, we need a vacuum chuck, which you can see here. There is a vacuum chuck, right. There is a vacuum pump. This goes to the vacuum pump, to vacuum pump. There is a spindle. There is a spindle which spins, right, and we said in starting there is a vacuum chuck here. Now, here the vacuum would be created here in this area center. This is the wafer. Wafer, we can also say substrate, right, and substrate is holded onto this vacuum chuck with the help of vacuum, and once it is attached or holded through vacuum, then we start dispensing photoresist. So, there is a photoresist dispenser. So, once the photoresist is dispensed, then we have to follow slow spin, ramping up, and once it is spin coated and it stops, we can see time, speed, the quality measures can be time, speed, thickness, uniformity and particle size. So, if you remember, the steps in photoresist is, first is your, after spin coating there is a soft bake. Soft bake, like I said, 90 degree, 1 minute, depending on type of photoresist. 1 minute on what? On hot plate. So, soft baking when we perform, what is the advantage of soft baking? What is the advantage of soft baking? First is partial evaporation of photoresist solvents. Second is it improves adhesion. Third is improves uniformity. Fourth is improves etch resistance. Then optimize light absorbance. Finally, characteristics of a photoresist, of course, there is a characteristic of photoresist. So, optimize light absorbance, improves etch resistance, uniformity, improves adhesion and partial evaporation of photoresist solvents. So, characteristics of photoresist can be defined if depending on is it bright field photoresist, is it dark field photoresist, and also what kind of mask you use. So, now we know what is the advantage of performing soft baking. After soft baking, we have to align the mask. First is load the mask and then align it with the spin coated wafer, right. So, when you align the mask, after that what you perform? You perform UV exposure. So, you should have a UV light source, you should have a UV light source. The ideal intensity pattern should be like this. However, the intensity on the wafer, the UV intensity on the wafer is somewhere like this. So, how it happens? There are few, this is a mask. Through the mask, when the UV light passes through, there is a straight refracted light. There is a lens here, and through the lens the light is diffracted and collected by the lens, right, which falls on the UV. So, lens diffraction after focus by the lens, right, and it falls on the photoresist coated wafer, and it cannot pass through the dark area, it can only pass through the bright area. It cannot pass through dark area, it can only pass through bright area. What cannot pass? UV light cannot pass, UV light cannot pass. So, after the photoresist is exposed in UV light, like I said, depending on the so after that depending on the mask and type of photoresist, we will obtain different pattern, right. So, how can we obtain? By developing photoresist in photoresist developer. So, the soluble areas of photoresist are dissolved by developer chemical, visible patterns appears on the wafer, right, either windows or islands, whatever we have designed, right. Suppose we are designing on the wafer some electrodes, then these are some islands, these are some valleys, right, or we are creating a pattern like this, which is your photoresist. Then this area we want to etch, this is your photoresist, this is your silicon, we want to etch silicon, right. So, this is a window that you have created, We will take an example in later class. So, when you develop the photoresist, if it is a normal development, you will get pattern which is shown here. However, there is under development, then you will get this kind of pattern. If it is incomplete development, you can see here. If it is over development, then you will see this structure. Okay. So, the time is very crucial. The time to develop the wafer in the photoresist or develop the photoresist in the photoresist developer is very important, is crucial, and if you exceed the time, then there is a over development. Sometimes there is a incomplete development if you take out the wafer before time, and then can be under development. Having said that, let us see negative and positive photoresist example, right, which we have just seen, but in form of schematic. So, if I have a substrate and if I coat this substrate with a photoresist, I have a mask here, you can see there are two dark areas, remaining there are bright fields, it is a bright field mask, or let us assume it is a bright field mask. Now, if I expose this wafer, if I expose wafer number 1 with UV light, right, then if it is a negative photoresist, the area which is exposed, you see the area which is this one, exposed will be stronger. You can see here, right, the area which is exposed is stronger in case of negative photoresist, while in case of positive photoresist, the area which is exposed becomes weaker. You see, the area which is exposed becomes weaker. Area which is exposed by UV light, right, that area the photoresist will get developed if it is a positive photoresist. You got it? Easy, right, very easy, right. It is a negative photoresist and positive photoresist. It is very easy to understand what will happen if I use a particular photoresist. We have just seen mask, we have just seen few masks, and these are master patterns which are transferred to the wafers. So, when you talk about types of mask, we have Fe2O3 on soda lime glass, we have chrome mask, these are two different materials, while the masks can be classified as bright field mask or dark field mask. This is an example of bright field mask. Okay, guys. Now, when we talk about mask, there can be defects in photomask. Defects in photomask. What are those defects? The first defect that you will see is a chrome spot. Now, for us, we do not care when we are going to make a bigger structure, when we are going to fabricate a bigger structure, but when we talk about MOSFETs, then within this area there can be thousands of MOSFET, right. So, we are losing those MOSFETs if we have the chrome spots. If we have chrome extension, we will not have correct results. If we have bridging, and if I am going to make a heater, it will be short, right. If I make a heater, let us say, and if there is a bridging, this is a short, the resistance would be different. Or let us say you have heater like this, right, and if I have short here, then it is gone, correct. So, chrome bridging is not acceptable. Next, pinhole, chrome is not there at all, not allowed. Then clear extension, you see, clear extension not allowed, right, because the value that we calculate and value when you use this mask would be totally different. Next is clear break, breakage is at all not allowed, right. If there is a break, let us say if I make a this pattern, right, and if there is this is a break, then it is not correct, right. The design itself will give us a different value if there is a break in the mask. So, these are few defects that you need to understand and need to observe whenever you start working with a photo mask. So, this is a video, interesting video, where you will be able to see the mask aligner, and it is an automatic mask aligner. So, yeah, I will play the video, look at it, it is a front to back alignment, and it is very interesting to see this mask aligner. Then let us talk after the videos that are here to follow, and then we will discuss for another 5 minutes to see what we have learned.
Hello, my name is Bernhard from the SUS Microtech development team. Today I'd like to present our new generation of production aligner, the MA200 Compact, which offers an advanced technology design, unmatched precision, and a high degree of flexibility. See for yourself how easy it is to operate. The chuck is stored in the bottom part of the aligner and is quick and easy to load. Equally easy to insert are the mask holder and the mask. Now I load the carrier. That's all there is to it, and the MA200 Compact is ready for operation. The processes of the MA200 Compact can be controlled via touch screen. For some processes, you can select between fully automatic and manual operation. A robot scans the wafers and determines their quantity, position, and size. And the processing begins. The MA200 Compact processes wafers and substrates up to 200 millimeters regardless of their material, size, shape, and thickness. The machine runs and adjusts fully automatically and is optimized for the processing of thick resists, such as with thick resist flip chip bumping, wafer level packaging, MEMS, nanotechnology, or telecommunication devices. The big advantage over steppers is the exposure of the entire wafer in one step. Thus, a throughput of more than 100 wafers per hour can be achieved with an overlay accuracy in the sub-micron range. Now, let's slow the process down and take a closer look. First, the wafer is pre-adjusted onto the pre-aligner in preparation for the ensuing alignment. A linear transport system loads the wafer onto the exposure chuck, which, together with the robot arm, guarantees the optimal and flexible handling of the substrate. No other mask aligner on the market offers a higher degree of alignment accuracy than the MA200 Compact. With the use of the recently developed and patent-pending Direct Align option from SUS, the mask is aligned directly to the wafer, guaranteeing an overlay accuracy of up to 0.5 microns at 3 sigma. The structures of the photomask are conveyed via shadowcast. The patented wafer leveling system from SUS compensates for topographic variations and wedge errors, thus guaranteeing perfect alignment and exposure results. And the entire process is easy to monitor here on the touchscreen. Because of the MA200 Compact's newly designed microscope, during exposure, the mirror housing doesn't move forward. The microscopes only move sideways, thus reducing the vibrations of the alignment stage to a minimum, resulting in far greater accuracy. The optics of the MA200 Compact are optimized for thick resist processing. In thin resists, it achieves a resolution of 3 microns in proximity mode and a sub-micron resolution in contact printing. A microscope for bottom side alignment is optionally available. It can process substrates with thicknesses of up to 4 millimeters. The MA200 Compact is a master when it comes to detail. Our idea while designing it was to create a device that is both user and maintenance friendly in order to further reduce your operational costs. The electronics and all important components are easily accessible, as well as being arranged in a clear and logical manner. Because of its compact size, it also saves valuable space in the clean room. The MA200 Compact is the ideal exposure system for application areas with high demands in terms of package densities and micromechanical structures. I can only recommend that you take a closer look at our new mask aligner in person and would like to invite you to do so today. The MA200 Compact from SUS Microtech.
Let us see this another video, and again this is on the Carl Zeiss MA6 mask calendar SOP. How to use a mask calendar, there is a video on this. So, let us see this video and then let us discuss.
This is the MA6. It's used to expose UV light to your substrate that has either photoresist on it. So before we run the machine, the first thing we got to do is make sure the light bulb is turned on or even not blown up. So we come out to the back and you can see the lights turned on by the reflection here, or you can see the light glowing. So you know that the light bulb is on. But in addition to that, you want to find out how many hours are left on the light bulb. So you check the power supply. So you hold this button called DS. And it says 3226. That's how many hours the bulb is being used. So the bulb has a lifespan of 4,000 hours. So when it's over 3,500, you would notify staff and tell them to change it. So we're pretty close to that. Now that the bulb is okay to use, and there's nothing wrong with the bulb and the power supply, we want to log into the system. So before we log in, we check the logbook. And the logbook would say that the last person who used it was Monica on 2/21. And then you would check what notes she had or anything was wrong. So you can see there's nothing wrong. So we're ready to turn the machine on and log in. So the login computer is here. You have to log in to use the machine, otherwise it won't turn on. And the login has several functions. The first screen is the login, where you type in username and password. You can schedule to use a machine at different hours. Also, you should check this to make sure nobody else is using it. So today is the 24th, and it's 10 a.m., and there's nobody using it, so we're free to use it. Also, there's a history tab where we can see the last user. And you can see that Monica was the last user, and she was the last one to write in the logbook. So once we know the machine's ready and it's okay to use, we just log in. So once you've logged in, the machine will be able to power up. And what we do now is we turn the on switch on here. So we just turn it to the on switch. And you can see the machine starting up. And it's important to read the screen. It tells you a lot of information. So it says ready for start, press load button. So the load button's right here. And we press that. And now it says, watch out, machine is starting up. You know when the machine is ready for load and started up when the information says ready for load. So before we run the machine, the one thing we can do is change the parameters. So you hit this button called edit parameter. And now you can adjust the parameters such as time and gap distance and type of exposure. So how do we edit the parameters or change the different parameters? We can use the X left and right. So we move this way. We can change the gap, change the type of contact, and then change the exposure type. So let's change the exposure time first. So it's at 5 seconds now. We can change it to 25 seconds. If you hold fast and up, you can change it faster. So it's at 25. Let's make it 26. Now we want to go slower, so we don't hit fast. We just... So now we've adjusted the exposure time. Let's change the alignment gap. Let's make that 40. And then let's change the type of... We'll make it soft contact. And now the parameters have changed. There's different types of exposure types, from soft, vacuum, hard. You can look at the supplemental to get more information. But right now we'll set it as soft. So once your parameters are set, you can hit edit parameter. What we're going to do now is load the mask. So how do we load the mask? We press the button called change mask on the screen. So when you hit change mask, you're ready to load the mask. So we put it in here. So you load your mask in here by lifting this clip here and putting it in. And when it's in nice, you hit this button called enter, and you can toggle the vacuum. So right now the vacuum is off. When you press enter, now the vacuum is on. And when you come back, you can see that it's vacuumed in and it's stuck pretty well. So now we're going to put this in here. So we carefully carry it. And we place it all the way in. And when it's in, we press change a mask. And that's how you load your mask. We're going to be doing a backside alignment now. So what this does is it aligns features on the back of your wafer to your mask. And how you do it is with the microscope from the bottom. the first thing we do is we have to have our mask loaded, and then we turn the screen on, and we make sure this thing says backside alignment microscope is on, so it's on. But also we need to change this to backside alignment. So it can be either a topside alignment or it can be a backside alignment. So this is an illumination. So now the light is coming from the backside. So if you look in here, you can see the light hitting the features. So that's the microscope from here looking up and light hitting it. So we can look for those on the screen now. And pretty much what you do is this controls the microscopes on the back. So you can select one at a time and move around till you find your features. It looks like we found our alignment marks on the mask. So we need to adjust the focus. So you use this top straight left and right. So the left one adjusts the left, and the right one will adjust the right focus. You can also adjust the intensity. And you can also adjust the position. So if I want to move this one up and down, I'll hit right, and then I will move it up and down. If I want to move the left one, it's a similar thing. So when you find your mask and you think you're ready to do exposure and align it, you would grab this image. So you press grab image button right here. And when you press that, what it does, it takes a picture of the mask. And now we're ready to load the wafer. We press this button where it says load wafer. So it says pull slide and substrate onto chuck. And we would just load our wafer on. And when it's in, you press enter, and it'll bring it up. So now you can see you're in contact. This is the image overlay from the mask. And these features right here, so they're the bottom substrate of your wafer. So how do you move the wafer? We know that these buttons move the microscope. So how do you move the wafer? It's these buttons, right? It's these knobs right here. This is the Y, the X is on this side, and this is the tilt. So I'll give you an example. I can turn this, and you can see the background, these images moving. And then you can see this moving. So this is the Y position on the left side, and on the right side is the X knob. And you can adjust the tilt with this too. And you can adjust the focus, and you can adjust the intensity or light. So you would do that to find your alignment marks and then align them. So once you have aligned them, you're ready for exposure. And how do you expose? You press first you alignment check, which will bring it up to touch. You want to make sure nothing moved. And then when it's in contact, you hit exposure. And then when you hit exposure, it's good to turn your back away from the light so it doesn't damage your eye. So we hit exposure, and then we just turn away. So after exposure, you need to unload your wafer. So what you do is you would come to the screen, and it will say pull slide or unload exposed substrate. So you just pull it out, and then you press the enter button, and then the vacuum will be released. And you can take your wafer out. And then you put it back in. So that's how you unload your wafer after exposure. What we're going to do now is topside alignment by using the microscope on the top to align to the wafer that's underneath through the glass. So to do topside alignment, we need to move the backside microscope. So we press this button, that turns it off. Also, we need to put the illumination to the top side. And then we can load our wafer in. So again, you press load, And it says pull, slide, and load substrate onto chuck. And you press enter when you do that. And the microscope will automatically come down because we have the BSA microscope light, button off. So now it's down, we turn the TV screen on. And what this is doing is taking putting the image from here onto the screen. So again, these buttons right here control the X and Y position of the microscope. So it looks like we found something here. So we can turn out, the power of illumination is pretty high intensity. So we can lower the power, and you can see that. So we gotta find the mask alignment mark on this side. So there's different functions on this. This knob right here. So if you move it, this will control the light microscope, the X position of the right microscope. And the left side has the same button. So when I move the left knob, I can turn this way. When I move the right knob, I can turn it this way. We can adjust the tilt to make these match up by turning this knob right here. So they look like it's pretty matched up. So what would you do is you would do the same thing as similar to backside alignment. You would align your alignment marks on your wafer to these right here. So you can see that if I move this, these knobs always control the substrate. So when I move this, you can see that this has been moved. So you can tell that's the actual substrate moving, not the mask. So you try to focus it, and you're trying to find your alignment marks and align them to the features. And then once you have aligned it, you do the same thing. You do alignment check, and then I'll bring the mask up, and then you would expose it. So you press expose, and then you do exposure again. So then you turn away so the UV light doesn't hit your eyes. So after you're done with exposure, you would unload your wafer. So it tells you pull, slide, or unload substrate. So you pull it out, and then you would take it out. And you finish your sample. You put this back in. Now if you're done, you want to move this back up and you don't want to bring it back down. This is where you press the BSA button. So by default, this will not come down. But also to bring this up, you press F1 and enter. And it will bring the microscope up. It's always good to leave it in this position with the microscope up and the BSA button on, because that way the microscope doesn't come on and up every time you're using it. So after that, we're ready to take out our mask. If we want to unload a mask, we press the change mask. It's pretty similar to loading it. It's a reverse process. You would press change mask. You would take your substrate out. You would hit the enter button to remove the vacuum. And then you would take your mask out. You would press the change mask button again. And it would say confirm with enter, as you know the mask is there. So now we're ready to turn the system off. So we want to make sure everything's in the standby position that you started the machine with. And then before you turn it off, you want to make sure you write in the logbook the different parameters. So the compressed air is about 4.9. The nitrogen is about 1.65. The vacuum is about 0.86, negative 0.86. We used a 4-inch wafer with silicon, and we did 25-second exposure. Now we're ready to turn off. First thing we do is we turn off the switch here, also the TV screen, and then we can log out here. And the some messages like, did you reset the X, Y, and tilt position? And we did that. So we put OK.
Okay. So, if you now see what we have learned, if you can see, I will show it to you on the screen here. I have something in my head. What we have learned today is a step called photolithography, the step called photolithography. In the last two videos, what you guys have seen? One is a automatic mask aligner. You have to load the wafer, it will perform everything, a robotic arm will take the wafer and then it will perform the photolithography. In the second one, you have seen how can you perform front to back alignment, how can you align the wafer, how you have to align the mask, what is the procedure. The idea is to fabricate simple things, simple devices like the one that I am holding in my hand, or complex devices such as MOSFET, or devices that can be used for clinical application like our drug screening device that we will be talking about in the lectures to follow, right. A drug screening device will look similar to what I am holding right now in my hand. This device can be used for rapid drug screening. That means that if a person comes with a cancer to a doctor, the doctor has to decide which drug he has to or she has to give to the patient and which will work out. But unfortunately, there is no patient centric platform that a doctor can try, that a clinician can try before giving it to the patient. That means what I am saying is, if you take the cells from the patient, you load the cells onto this device, you flow the drug, you get the results and tell which drug would be effective for this particular patient. Can you fabricate this kind of device? The answer is yes. How? By understanding photolithography. Right. So, we will be looking at such kind of device, such kind of interesting platforms that can be used for rapid drug screening. Why I said rapid drug screening? Because there are multiple channels here at a single in a single shot we can perform 8 different drugs we can screen using this platform, or we can check 8 different patient samples with single drug. So, such kind of applications we can use it using the microengineering platform and understanding the photolithography. So, just go through this particular module and try to understand, try to focus and see what things we have been discussing in this module, and if you have any questions, feel free to ask me in forum and either me or my TA would reply to your queries. Let us see very interesting applications of this microengineering devices in the classes to follow. Till then, you take care, have a nice day.